I think most people who clicked on this video would agree that math is pretty beautiful. But sometimes we get so deep in the weeds that we forget the larger picture and the connections between what we're doing and other areas of math. The connections which play a large role in making math as beautiful as it is. In a second, I'm going to share with you a problem. And at first, it will seem like a simple geometry question that perhaps you may have even asked yourself at one point. But actually finding a solution turns out to be surprisingly difficult. It will require us to take a step back and see just how related all of math is. So here's our problem. Say you have a square piece of paper and you want to divide it into triangles of the same area. The question is, for what numbers of triangles is this possible? For example, even though the configurations on the left do not work for 8 triangles, since the triangles don't have equal area, 8 triangles is possible because all the triangles on the right triangulation have the same area. I'll give you a moment to pause and think about this question. Or even better, pull out a pencil and paper and try it for yourself. This problem seems so simple that it's hard to even know where to get started on solving it. So let's just experiment with small numbers of triangles to better understand what we're dealing with. For simplicity, say we have a unit square. Then take t to be the number of triangles we wish to divide the square into. This means if t triangles were to work, we would need a configuration with each triangle having area 1 over t. We'll keep a running tally of which t work on the left, running from t equal 2 to t equal 6. Let's begin with 2 triangles. This works since we can divide the square along a diagonal, leaving 2 triangles with area 1/2. With 3 triangles, we can divide the square like this or this. But in both cases, one of the triangles has area 1/2, so these arrangements won't work. We could keep searching for a solution, however after a bit more fiddling around, we might suspect that it is impossible. Since we haven't proven this, I'll denote it with the red question mark. t equal 4 is pretty simple. Here are 2 triangulations that work. In fact, we can form a general solution for all even t just by adding more rectangles to the second configuration. To be more precise, we can make t over 2 equal size rectangles and divide each rectangle into 2 triangles, leaving us with t triangles of equal area. Therefore, t equals 6, t equals 8, t equals 10, and so on all work. For 5 triangles, messing around reveals no obvious solution, and since it's difficult to exhaustively check all triangulations, we'll just use our red question mark again. At this point, we have found a solution for all even t, and there is no obvious solution for small odd t, so we might conjecture that even t work and odd t don't. But let's take a second and think about whether this conjecture makes sense. There doesn't seem to be anything about odd numbers that makes them inherently not work. On the other hand, as you increase the number of triangles, there are more and more ways to triangulate a square. It seems unreasonable then to think that out of all of these possible triangulations with an odd number of triangles, we would never be able to find one with the triangles having equal area. But miraculously, the conjecture actually turns out to be true. So we've examined the problem by looking at examples of small numbers of triangles and noticed a pattern. From this pattern, we formed a conjecture, and now let's see if we can prove it. Take a second to think about some possible solution paths on your own. After messing around with the problem, you might come up with a few possible paths to prove our conjecture. Some of my initial thoughts were to generalize an argument that works for small odd numbers of triangles to all odd numbers. Or perhaps we could somehow use a powerful geometric result like Euler's formula. If you try these ideas, it becomes clear that one of the main reasons the problem is difficult is because it is surprisingly hard to translate the equal area condition into something that's easier to use. In fact, There's only one known way of proving this conjecture, discovered by Paul Monsky as recently as 1970. At least for me, this is surprising, since the problem could have easily been asked over 2,000 years ago by the ancient Greeks. And while I'd hope you agree that this question deserves to be answered, the real beauty of the proof, and what really justifies our journey, is the pauses it makes in seemingly distinct areas of math. Let's begin our solution by discussing a result from graph theory called Sperner's lemma. Let's say we have a triangulated polygon, and we color all the vertices one of three colors, say red, green, and blue. The triangles that the lemma concerns are those with three different colored vertices. So let's call these triangles colorful, and we'll color them yellow. We also care about segments between adjacent green and blue vertices, which we will color turquoise. So we currently have one colorful triangle and 6 turquoise segments. Assuming that lines cannot contain more than 2 colors, Sperner's lemma says that the number of turquoise segments on the outside of any triangulated polygon is congruent to the number of colorful triangles inside modulo 2. In other words, the number of colorful triangles and the number of turquoise segments on the exterior of the polygon are either both odd or both even. I encourage you to take a moment and try to experiment with some triangulated polygons and perhaps come up with a proof on your own of Sperner's lemma. As a hint, you'll want to count turquoise segments in 2 ways. One way to count turquoise segments would be to add the number of turquoise segments on every triangle. However, if we list a few possible triangles, we notice that only colorful triangles have an odd number of turquoise segments. I encourage you to play around and convince yourself that this is always the case with our assumptions. Using this, if we go triangle by triangle, starting with the top left, and count the number of turquoise segments we see, the number of segments we will count has the same parity as the number of colorful triangles. On the other hand, counting in this way counts every turquoise segment in the middle of the polygon twice, so these do not affect the overall parity, while it counts those on the exterior of the polygon only once. Putting these two ideas together, we can say that the number of colorful triangles is congruent to the number of turquoise segments on the exterior of the polygon modulo 2, completing our proof. It might be hard to grasp why this could be useful, so let's just summarize what it would mean for our square. Sperner's lemma allows us to use only information about the outside of the square, the number of turquoise segments, to tell us about the unknown triangulation on the inside, the number of colorful triangles. This would simplify our original problem by giving us something that's essentially constant across all arrangements of triangles inside the square. What we ideally want then is a tool that allows us to somehow connect colorful triangles to our equal area condition. If we could make such a connection, then we would have nearly solved the problem by allowing us to only look at the outside of a square in order to learn about the areas of triangles within. To find such a tool, we will have to take a detour into the land of valuations. In order to put labels on things, let's move our square into the Cartesian plane with vertices 0, 0, 1, 0, 1, 1, and 0, 1. Then we will eventually color the vertices of the square with 3 colors by assigning values to both the x and y coordinates of each point using a function called a valuation. The color will be determined according to the relative sizes of the x and y outputs. So what is a valuation? It is essentially a function, say v, that has to satisfy a few special properties. For now, we will look at valuations that take inputs from the rationals and output non-negative rational numbers back. A valuation has to satisfy 3 special properties. V of x is 0 if and only if x is 0. It is multiplicative, meaning v of x times v of y is equal to v of x times y, and it must satisfy the triangle inequality. While these rules may seem arbitrary, they are similar to the rules that define distance metrics. In other words, if you were to create alternate ways of defining how we measure the distance between two numbers besides the usual absolute value function, you might want rules like these. The most familiar valuation to us is the absolute value function, and it's pretty easy to see that it is a valuation. In other words, it satisfies all three of these properties. But unfortunately, the absolute value is almost too nice for our purposes, so it won't give us the information we need while coloring points. So instead, let's turn our attention to a family of valuations called the p-adic valuations. Each p-adic valuation is based on a certain prime p, which we can choose. This means there are actually an infinite number of p-adic valuations. Then, say we have a rational number we wish to evaluate, such as 24/7. We can write, for example, the two-adic valuation of 24/7 as v sub 2 of 24/7. In order to find the number this corresponds to, we factor all the powers of 2 out of 24/7. The two-adic valuation of this is just 2 to the negative 3, or generally 2 to the negative of the exponent. For a number like negative 11/4, we write it as 2 to the negative 2 times negative 11. So the two-adic valuation is 2 squared. And if there are no powers of 2, then the two-adic valuation will be 2 to the 0 or 1. This process of factoring out the powers of p and negating the exponent is the same process we apply to any prime and any rational number. As a general formula, the p-adic valuation of a non-zero rational number r, expressed as p to the n times a over b, is p to the negative n. In this formula, we're assuming that we factored all powers of p out of r. In other words, a and b aren't divisible by p. We have to define the p-adic valuation of 0 separately, so we'll say this is 0 for all primes. In fact, what we have covered so far is enough to show that p-adic valuations indeed satisfy all three properties of valuations. The first two properties are actually pretty easy to show, and I encourage you to pause the video and prove those for yourself. However, the property that is the most important for what we are doing turns out to be the third property, the triangle inequality. While for absolute values we tend to think about this property geometrically, we don't yet have a geometric intuition for p-adic valuations, so we will have to rely on other methods to examine it. Let's take an example to see that this property works. Say x is negative 11/4 and y is 24/7. So we can calculate x plus y to be 19/28. As we previously established, v2 of x is 4 and v2 of y is 1/8. And we can find v2 of x plus y to be 4, which is of course less than 4 plus 1/8. But we actually have an inequality stronger than the triangle inequality for two-adic valuations. It turns out that v2 of x plus y is at most the maximum of v2 of x and v2 of y. In fact, this inequality actually turns out to be true for all p-adic valuations and is known as the non-Archimedean property. The proof that p-adic valuations are non-Archimedean just involves a bit of algebra, so we won't go into it here, but I encourage you to try proving it on your own. One of the main reasons the non-Archimedean property is useful is, with it, we have an even stronger result when the p-adic valuation of x is not equal to the p-adic valuation of y, and that is vp of x plus y is equal to the maximum of vp of x and vp of y. This is a pretty interesting and powerful result, so let's prove it. Since x and y are interchangeable, we can assume without loss of generality that the p-adic valuation of x is less than the p-adic valuation of y. Then we can note two things. Firstly, that the p-adic valuation of x plus y is at most the p-adic valuation of y. and secondly, that the p-adic valuation of negative x is strictly less than the p-adic valuation of y. Then Vp of y is at most the maximum of Vp of x plus y and Vp of negative x. But since both Vp of x plus y and Vp of negative x are at most Vp of y, we know this maximum is at most Vp of y. However, now we have the p-adic valuation of y on both sides of the inequality, so we know that both of our inequalities are actually equalities. And since Vp of negative x is less than Vp of y, this equality is only possible if Vp of x plus y is equal to Vp of y, which is the maximum of Vp of x and Vp of y. It turns out, with an induction argument, this can be generalized to say that if Vp of a is strictly greater than Vp of bi, the p-adic valuation of the sum b1 plus b2 plus so on plus a is equal to Vp of a. In other words, the valuation of a sum just takes the maximum valuation of a number in the sum, as long as that maximum is unique. Okay, obviously all of this stuff on valuations is a lot to think about at once, so let's just summarize some of the main points we made about p-adic valuations. P-adic valuations can be evaluated by factoring the powers of p out of any rational number. They are basically functions that satisfy a few special properties. They are zero if and only if the input is zero, they're multiplicative, and they satisfy a stronger version of the triangle inequality known as the non-Archimedean property. The non-Archimedean property is particularly useful because it shows us that if Vp of a is greater than Vp of bi, we have this equality. From now on, we will be working with two-adic valuations. The reason we choose two-adic valuations is because we are trying to distinguish between odd and even numbers of triangles, so it makes sense to look at two. When we color a point P, we will do so based on whether the two-adic valuation of 1, the two-adic valuation of x, or the two-adic valuation of y is the largest. Let's say if the two-adic valuation of x is the largest, we color the point red. If the two-adic valuation of y is the largest, we color it blue. And if the two-adic valuation of 1 is the largest, we color it green. Here's what the coordinate grid begins to look like for points with rational coordinates. However, with what we have defined so far, we are limited to dealing with rational inputs for two-adic valuations, which won't allow us to evaluate points with irrational x and y coordinates. We could of course go back and try to find another valuation, but this isn't as big of an issue as you might think due to something called Chevallier's theorem. This allows us to basically extend the p-adic valuations to all real numbers. This theorem does not uniquely define such an extension, so we still might not know the valuations of specific points, but all we need is for this extension to exist. There's a link in the description for a more formal statement if you're interested. So finally, let's take a look at our triangulated square and color some of its vertices. For 0, 0, the two-adic valuation of 1 is the greatest, so this point is green. Similarly, the points 1, 0 and 1, 1 will be colored red, and 0, 1 will be blue. We unfortunately can't color the interior vertices since we don't know their exact coordinates. Now, let's suppose our square were to have a colorful triangle. Then we'll take a look at its area. Say our red point has coordinates x or y r, our blue point xb, yb, and our green point xg, yg. If you know some linear algebra, you can calculate the area of this triangle using the following formula involving the determinant. Now let's take the two-adic valuation of this. Notice the absolute value won't affect the valuation since v2 of negative x is the same as v2 of x, so we can get rid of it. Next, from our definition of coloring points, we can say out of the 6 terms in our sum, x or yb has the greatest two-adic valuation. So from our formula earlier, the two-adic valuation of the determinant is just v2 of x or yb, which we can see is at least 1. Therefore, we can say that v2 of twice the area is at least 1. Our first noticeable consequence of this inequality is that any line can have at most 2 different colors on it. If it had 3, then there would be a degenerate colorful triangle on that line. In other words, a colorful triangle with area 0. But because the two-adic valuation of 0 is 0, it doesn't satisfy our inequality, so 3 colors on a line is impossible. So now let's try to use Sperner's lemma by counting the number of turquoise segments on the edge of the square. Because only 2 different colors can be on any line, no matter where we place vertices and what color they are, only segments on the outside of the square between the green and blue vertices can be turquoise. In fact, no matter how many other vertices lie on the side and whether they are colored blue or green, the number of turquoise segments on the blue-green edge will always be odd. This means we can apply Sperner's lemma and know there must be an odd number of colorful triangles, and in turn we know that there must be at least one colorful triangle. Now we're on the home stretch. If we assume every triangle in the triangulated square were to have an equal area, we need this colorful triangle to have area 1 over t. From our earlier inequality, we have v2 of 2 over t is at least 1. But for odd t, the left-hand side evaluates 2 to the negative 1, or 1/2, since the denominator isn't divisible by 2. This inequality is a contradiction though, so a colorful triangle cannot have area 1 over t when t is odd. Since there is always a colorful triangle, and this colorful triangle cannot have area 1 over t, there is never a triangulation of a square into an odd number of triangles where each triangle has equal area, finally finishing our proof. Let's pause for a moment to appreciate how we arrived here. We took a geometry problem and analyzed a certain function related to primes to color the vertices in a clever way. This in turn let us use a combinatorial result to show that there is a triangle that doesn't have equal area. Thinking back to the question we asked, in many ways it's hard to believe that we had to explore so much just to find a solution. And while this proof is undoubtedly beautiful, it leaves many questions unanswered. What is special about a square? Would this work for other quadrilaterals? Or other polygons? Or even other dimensions? There are also deeper questions about the math we use that this proof raises. What is unusual about p-adic valuations? Why not some other valuation? And why do we even need to dive into valuations to solve a problem that is so easy to state? I would have loved to answer some of these questions in this video, but what we have done is already enough to chew on for today. So instead, I encourage you to look into these questions on your own. Some links of resources I found during my research are in the description if you are interested. But otherwise, I hope you enjoyed and thanks for watching.